Thank you for the invitation to speak here at Big Data Scala. I'm very happy to come here, in particular, since essentially big data has been, of course, one of the poster childs for Scala adoption recently, like Mike said. And I would like to explore a little bit how, in particular, SPARC and Scala are connected and how we can help each other and how we can work together to do something good. So Scala, of course, I guess everybody here knows Scala very well. So it's a functional language. It's object-oriented, statically typed, and it interoperates well with Java and JavaScript. But I want to essentially look a little bit beyond that and say, well, that's just essentially the point it is in the languages space. So what is really the important invariance in the language that you say, what's sort of the philosophy, the spirit behind Scala? And I think there are actually two. And the first invariant was always it should be a scalable language. That's actually part of the name even. And with scalable here, I mean that it helps people essentially grow their own languages. So languages, Scala is not a language that is very opinionated, that tells you have to program exactly this way. That's both its strength, and some people would say that's a shortcoming. Not everybody wants a non-opinionated language, but it has led to a lot of very, very good things, and one of them was SPARC. So what the language has to enable this growability is it has very flexible syntax, flexible types. It has user-driven, user-definable operations, high-order functions, implicits, and so on. And all these make it very easy to create your own domain-specific languages on top of Scala. Let me just, Okay, so, and that design had a spectacular success, you could say, because over the years there have been lots and lots and lots of very interesting domain-specific languages on top of Scala. So SPARC is one of them. Chisel is another language coming out of Berkeley for hardware design, and the latest RISC-V processor, which is a very neat processor, has been designed from the ground up with Chisel, as well as many other things. There, SBT, like it or hate it, it's a Scala DSL. Akka is a Scala DSL. The testing frameworks are that, and so on. So a lot of DSLs have come up, and SPARC is one of them. So it's a domain-specific language. It's implemented in Scala, and it's embedded in Scala as a host language. So essentially, you can see SPARC as just a library running on top of Scala that gives you a new language interacting with both Scala and SPARC. So if you look at the architecture diagram, then here you see you have the SPARC runtime that is implemented in Scala. So it uses the Scala runtime, which in turn is implemented on top of the JVM. So it uses the Java runtime here. And the SPARC runtime, it interacts with both the file system and a cluster manager such as Yarn or Mesos. But that's actually not the whole picture. So if you look at it in a little bit more detail, then you see there's actually a layer on top of SPARC. At least if you consume SPARC from Scala, that's the picture. So there's actually the Scala REPL, the read eval print loop, sitting on top of SPARC. And that read eval print loop would essentially, you would type a query. The query would go into the REPL. The REPL would go to the compiler and say, compiler, please compile this query into Java bytecodes, which the compiler will oblige to do. Once that's done, essentially you load the class file, and that class file then would use the Scala runtime and do its magic. So SPARC, in fact, at least the Scala mode of SPARC, is really embedded much deeper than just another library into the Scala ecosystem. It actually reuses the Scala REPL and the Scala compiler as well. Now, if we look at DSLs, actually, for me, there are two major reasons why you might want to do a DSL. One reason is you have an idea for essentially a new syntax for a language, new operators or things like that. And Scala has a very flexible way to define this syntax, so a lot of people create DSLs that way. The other major reason is to say you want to essentially take the functionality of what you compute to a new dimension. Let's say from a single computer to a whole cluster. as is the case in SPARC. And that to do that, you need to have essentially a non-standard compiler pipeline or execution pipeline, not what you get in the standard Scala distribution. For me, actually, I find the second use of DSLs much more interesting than the first, because the first is just syntax, and syntax is actually always pretty shallow, whereas to essentially take the idea of computation into a completely new place and do something that people haven't done before is really fascinating. So what kind of a DSL is SPARC? Well, SPARC is very much in the second category. You could say, if I squint my eyes a little bit and look at SPARC, what is it? Well, it's centered around Scala collections. It essentially provides you immutable data sets called RDDs, for resilient distributed data sets, and they are equipped with functional transformers. And what are these transformers? Well, the most basic ones are things like map, reduce, flat map, filter, fold, aggregate, union, intersection. That's sort of the typical things you start out with in SPARC. And interestingly, you have the same operators no matter whether you interact with SPARC from, let's say, Scala or Python. They're named all the same, and that's very, very good, because essentially it gives you a common understanding and it makes it easier to switch the language. So have you seen these operators before? And the answer is, well, I guess most of you have. They are just the standard operators of Scala collections. They're exactly the same operators in Scala collections. So one way to see SPARC, a bit provocative, is to say SPARC is nothing but Scala collections running on a cluster. Great. So is that the whole truth? Well, not quite. There are actually several differences. I think the two most important ones are that the fundamental nature of the collections in SPARC and Scala is different, at least if you take the default Scala collections. So we'll see that the SPARC collections are actually lazy, whereas the Scala collections are strict. And the other major difference is, of course, that the operators I've shown you, they are some part of SPARC, but SPARC has actually other very useful operators, in particular around pair RDDs, where essentially you see a collection as having some sort of key and some sort of data associated with the key. And these currently are not part of the standard Scala collections. And one of the outcomes of this talk is to say, well, maybe they should be. I think that's probably a good idea to have these. So let's look at the first one first. SPARC is lazy, Scala collections are strict. So generally, if you do a collection library, you face a number of design choices. First design choice you have is, do you want to be imperative or do you want to be functional? So one very successful collection framework that's imperative is the Java util, the Java util collections, where essentially the fundamental operations are you have a collection and you can iterate over it. So a collection will give you an iterator, so you can go through it. And then the second fundamental operation is add. You can build an operation, you can build a collection by adding elements to it one by one. And that's, of course, an inherently imperative thing. You work element-wise, and the collection gets mutated by the add. In contrast to that, functional collection frameworks have immutable data sets as the fundamental data type. And then what they give you is essentially transformations that transform one collection into another using things like map, reduce, filter. And the probably most popular or widespread example of a functional collection framework is Scala collection immutable. There are others as well. So once you have a functional collection framework, you have essentially design choices what kind it should be. And the first is strict. That's what we have in Scala. Second one is lazy, which actually seems to be a bit more widespread. So C# has lazy functional collections, and so has SPARC. And the third one would be lifted, and a good example of that is the new Java 8 streams. So let's see what the differences are. So here I have a simple example where I have some data and I map them with a function f yielding a set or a sequence xs, and then I filter this collection, and that gives me ys, and then I take 10 and that gives me zs. So in a strict collection, the map is actually evaluated only once here. So I evaluate the map, I get the xs, and then I use the xs in my computation of ys and zs. Whereas in a lazy computation, the map is not evaluated at all when I write it. Essentially, all I get is a recipe to say, if ever you want to get the result of this collection, then here's how you do it. And I need the result twice. I need the result once for the ys and once for the zs. So I will actually go back and compute the map twice. The advantage of being lazy is that you don't need the intermediate list excess because that's not, that never needs to come into existence. So that means you don't need to build up these intermediate collection structures, and that means that lazy can be faster than strict because of that. It can also be a lot slower, namely when you have to, when you do a lot of needless recomputation of these things. So lazy demands that you are smarter about what you recompute. Okay, so let me maybe just launch into Eclipse to show you that. Let me just put this up that we can see the example. All right, is that visible? Okay. Okay, let me just go back to that one. I just want to do it step by step, so we'll get there. Okay, so here I have an example which is actually due to Eric Meyer. Eric Meyer had a very well-read ACMQ paper which says essentially if you need to be functional, you need to be purely functional. So almost functional programming doesn't work. And those were his examples. Actually, I think what he meant to say, and we talked later afterwards about it, is that you need to be very careful to mix laziness with imperative programming. So here you see a simple example. We have a list, and we have two predicates. One says the element is less than 30, and the other says it's more than 20. And just to see what goes on, each of these tests actually prints out what it computes. So if I go and now apply them, let's say with two filter operations, then I get what I would expect here. So I have the list here. Then I go through all the elements of the list, ask for each one of them, are you less than 30? And then for the remaining elements here, I ask each one of them, are you more than 20? And if I then print the list, then nothing more happens because the list is evaluated. So let's do something slightly different. Scala actually has lazy collections, just like SPARC, but you have to demand them explicitly by calling view on a collection. So if you call the view method on a collection, it says from now on, I want this collection, all operations on this collection to be lazy. And it's sticky. So if you perform a map on a view, you get back a view and so on. So if you have the view here, then you see nothing gets computed. I just have a sequence view. And if I do a filter, I still have a sequence view. The F here says that there's actually a filter operation as a last operation on the view. And still nothing changes if I do the second operation. So when gets something computed? Well, the first time I actually need the elements to do something else with them. So here that would be when I do the print on. So here now all the computation happens, and you see furthermore it's actually interleaved. So the order in which things happen is not immediately apparent for a programmer. So you have less more, then you have two lesses, then a more, and so on. Well, if you think hard about it, you probably will figure out why it is in that order. But it's not something that is immediately clear to people here. Okay, so one problem if your order is not, the order of operations is not completely clear to you is once you have effects like side effects, you're often in for a surprise. So, because of course for a side effect, it's very important to know when precisely the side effect happens because that effect will interact in time with all the other side effects in your program. So just to demonstrate that, we do a very simple side effect, that's an exception. So I go back to the normal program, and then here we have a new map on my excess list. and it says, well, I want to essentially do 1 over element in the list, each element in the list. Well, that could give me a division by 0, of course. So I want to catch that here in this last line and say, well, if that happens, then I just want to return the empty list, not do anything there. Okay, so we can run this, and if we do, if we then print the elements, then, well, that's what we get. So in the normal situation, we just get the empty list. Why? Because, well, we indeed had a 0 here, so 1 over that 0 caused the exception to be raised, and that the catch clause here gave us the nil. So let's see what changes if we do a view. So we get the same computation, and, well, we still get the view here because we didn't really need the element in that list. So we have a view, okay, and once we start to print, whoops, we get an arithmetic exception, division by 0. So even though you thought you caught the exception here, you didn't, because what happened here is not the actual map computation. It was a recipe to give you the map computation. The map computation happened here, where you probably didn't expect it when you went through the println statement, and that println statement wasn't guarded by a try-catch, so the exception escaped unchecked. So these were essentially Eric's examples to say, well, if you have lazy collections, be careful. And essentially he argued, well, the C# design to make the collections lazy wasn't actually a very good one, because all these are essentially traps and pitfalls for C# programmers. But on the other hand, if you are in a purely functional setting, like SPARC is, then actually being lazy is a very, very good idea. So that shows you sort of the trade-off to say, well, lazy collections are a very good idea if you're in a purely functional setting. They are a more dubious idea if you allow for mutation. Scala has both. And I think because Scala is over the years becoming more and more functional, so that means the mutation plays a less important role now, I think we should re-emphasize this lazy collection view in Scala. So let me just get back to the presentation. Okay, so what then is the last, is the later thing there, the lifted thing. So lifted is, one good example of lifted is what Java 8 does. So lifted means that your collection operations actually are neither strict nor lazy, but what your map and filter and things do is essentially really define a computation only, and you have to link that to a collection in another explicit step. So in Java 8, what you would write is you have a collection, and then essentially you get on the level of recipes, which is called streams in Java 8. So you have to turn it explicitly into a stream, and then on the streams you do a map. So another way to see that stream is just another fancy sort of iterator. And what the map gives you is another stream, but a stream is not a collection. To go back into a collection, you have to do a thing like collect. And here, the collect in Java 8, you have to give the precise type of collections that you want to go back. So you have xs.stream.mapf.collect. The advantage of that is that it's made very clear where you're on the level of recipes. That means no reuse, just computation, and where you're on the level of data. The disadvantage is it does add quite a lot of boilerplate, in particular for simple tasks. And if you're like me, then I probably write as many maps as pluses in my program. So these things matter. So essentially having needless boilerplate for a map is annoying. It would be like if I told you, well, no, you can't write plus, you have to write integer dot prepare for addition dot add dot map back to integer. You would say, you're crazy. No, that's way too complicated, of course. I don't want that. But if you write as many maps as you write pluses, then essentially the same argument applies. Okay, so what Scala can learn from SPARC here, is, I think, two main things. The first thing is I think we really should redo views for Scala collections. So views are currently not loved a lot, which has to do with the fact that some of the design, it has some rough edges. In particular, some of the views force you into, become strict surreptitiously. So because essentially views, one problem with views is that they support the whole collection API, and some of the operations you can't really do in a lazy way. And that means that these views become suddenly strict and people are surprised, and then they don't trust views anymore because they don't know whether they will be always lazy or not. So I think we should actually change them, and there is a scope for changing them because I think because of these problems, not many people are using views right now. So I guess we can afford to do some breakage, to have some backwards compatible breakage and design views pretty much like they would be designed in SPARC. The other thing we can learn is that what's really good is to control persistence explicitly. So SPARC for that has the cache operation, where you say you have this view, the computation, and to avoid things being recomputed, you have cache or persist, which says essentially take a snapshot of what you currently have, and from then on going forward, take the snapshot, but not the computations that led to it. And I think that's a very, very good idea that we should copy for the base collections in Scala. The other thing I think we should do is operations like reduce by key, group by key. Not only are they more efficient than the Scala equivalents, which is essentially group by, go into map, do a map values or something like that. They're also much easier to read and understand. So I think that's another obvious good idea. We should have essentially a notion of what a pair collection is, similar to what SPARC does, an implicit conversion from essentially collections over pairs to these pair RDD operations, just for essentially general collections, not just for RDDs. Okay, the second thing that I want to talk about in the Scala language is the second invariant, and Scala is really about the types. So most of the gray cells that went into the Scala designs were about designing the type system. The rest is comparatively easy because essentially we were able to profit in the runtime from the JVM, so not a lot of work had to go into the actual runtime, and essentially syntax and parsing and these things are always easy. So the types are hard because essentially there's a trade-off between safety and flexibility or ease of use. You can make your type system super flexible and super easy to use by just having one type called any or dynamic. So then essentially you can do whatever, but the system wouldn't be very safe. Also, there are type systems that are extremely safe up to the point where essentially you can encode total program correctness. These are then usually called theorem provers, so examples are Coq or Isabelle. And the problem is that I think it's still fair to say that it wouldn't hurt to have a PhD to use them. I don't say you are required to have a PhD, but it wouldn't hurt to have a PhD to use them. So they are not that super easy to use. And of course, the goal in type system design is to push the envelope, to say, well, we want to essentially at the same time become safer, and we want to be easier to use. And because it's a trade-off, you sort of choose where you get the bulge out here. So typical research in type systems lately has chosen to essentially push here in the vertical. So essentially that's all the work that led to the theorem provers we have now, or languages with dependent type systems like Agda or Idris, they are up here. So to say, well, essentially we assume that people are very comfortable with complex type systems. Let us put those type systems to use to get something that's safer. And that was this trend in safety. You could say Rust is actually another example, great example of that, where essentially for Rust the challenge was, can we get a type system that makes memory allocation safe without having essentially the escape hatch of a garbage collector. So if you only have malloc and free, can we essentially make a type system that makes this safe? And Rust largely succeeded with that, but you could argue at the price of some usability and complexity. People reportedly say using Rust is actually not so super easy, but of course for many the trade-off not having to use a garbage collector is worth it. So you could say that's a trend in type systems. The trend in Scala has been a little bit different. In Scala, actually, we were much more worried about flexibility. We were much more concerned about getting a type system that it's easy to use. So the main motivation here was to say, well, essentially, we know Hindley-Milner and we know these type systems of ML and Pascal and languages like that. Can we sort of get something that first interoperates well with Java, and second would be appreciated by somebody coming, let's say, from Python or Ruby, so people who are actually not used to static type systems. That was sort of the gamble and the challenge that we took, and that's why a lot of the essentially specifics in Scala type systems go more towards the area of flexibility. We'd like to move it up in the area of safety. In particular, I'd like to be able in the type system to define or to declare whether something is purely functional or not. And that would then also make the views safer. Then you could say, well, use views if things are purely functional, but once you have effects, then it's a bad idea. But we're not there yet. So that's essentially future research. So why do I talk about the types here? Well, it's because SPARC, as we know, is a multi-language platform. Several programming languages that are supported, I think currently roughly in order of popularity. Python is the most widely spread, then Scala, Java, R, and probably in the future there will be others as well. So one question to ask is, well, why would we recommend that somebody uses Scala instead of Python with SPARC, because SPARC has a perfectly good Python API. It has very good Python tools. So why Scala? So for me, I think there are two reasons. The first is kind of obvious. Well, Scala is native to SPARC. SPARC is written in Scala. So if you want to embed SPARC, let's say, in a bigger system that uses not just essentially the REPL, but essentially uses SPARC as a system component, then probably you have a much easier time using Scala than using Python for these things. But the second one, and I think that also applies to the data scientists, is that I do believe that types help a lot. So in my own experience, which is mostly about Scala collections, not about SPARC, but I've argued they are basically the same thing. I would never, ever consider using collections without the types. They're just too helpful to do without. So why is that? Well, functional operations, if you have functional transformations of collections, then there are no hidden dependencies. There are no side effects, no backwards channels where you don't know what goes on. Everything is out there. Inputs of these operations are parameters and outputs are results. So if you have a statically typed language, then everything that goes in and out of a transformation is checked by the type checker. And it turns out that the type checkers of languages in these collections are surprisingly good. So that means that typically, if you have a logic error or just a typo or things like that, typically it will lead to a type error immediately. So you don't even have to run the thing. You don't even have to figure out what they do. The compiler will tell you, well, you gave me this type, but I needed this other type. So logic errors usually translate into type errors. And that means that you can write programs that are literally hundreds of lines with these collections or SPARC. And once all the type errors are fixed, the chances are very, very high that your program will run. If you don't have the static types, that's of course not true. Then essentially you run your program and then debugging starts and says, well, why did I get this weird thing? So I think in particular when you work with collections, with functional collections, types are sort of the poster child. That's the poster child of essentially smart use of types, where types really, really help. That's why I think that I would also recommend to a data scientist to say, look, use a language with a static type system, with a precise static type system. It really helps you. Good. So that's essentially the spiel for the why, how SPARC and Scala relate. Now I want to talk a little bit about essentially what Scala can do to help SPARC further, because I think SPARC is a like Mike says, a killer app for Scala, so we should think about essentially how can we get the best out of it by helping each other. And I have 4 topics here. That's the infrastructure, in particular REPL, Spores, Fusion, and staging. So let's look at the infrastructure. So here's the picture of the SPARC runtime again. So I've already argued that SPARC reuses and repurposes a lot of the Scala runtime, the REPL, concurrency abstraction, serialization, and so on. So what we want to make sure is that those standard components work well out of the box and no forks are needed. One example for that, currently SPARC uses a fork of the Scala REPL because there was an incompatibility with the versions of JLine used. So essentially the SPARC is bound to one version of JLine for other reasons, and the Scala REPL used another, so you couldn't use one with the other. And that's sort of a fairly trivial engineering problem. Somebody just has to do it to make essentially the Scala REPL work with a foreign version of the JLine. So what Typesafe did is to say, well, we make that a high priority thing, and we make that change. And hopefully, I think we're on track to actually be able to roll back the standard REPL into the SPARC distribution. And I think that's generally something where I want to appeal to essentially both sides to say, well, that's really something we should be doing actively, because nobody wins by forking. We really need to have essentially the standard components, because only by doing that you get the bug fixes, you get the improvements down the line. So forking is essentially always, it might be a good idea for tomorrow or for the next month if you're in a deadline, but in the long term it's almost never a good idea. The other thing where I believe SPARC can help, Scala can help SPARC a lot is in the problem in the area of serialization. So one problem here is, in particular, is closures. So closures use Java serialization, and that can drag a very, very large dependency graph. So here's an example. Let's say you have a class C, and it has some field data which is drags a very, very large collection, a list or something else. And then there's a sum field, which is just the sum of the data. So that's just a simple int. And then you do at some later point, and you pass to this do later function a closure which says, well, I want to print the sum. I just want to print that sum. So you would expect to say, well, that shouldn't be a very expensive closure. But in fact, it is, because what happens is that the compiler, when it serializes this closure, it will serialize a pointer to the enclosing class C. And that pointer transitively can refer to this very large data collection. And that means that that very large data collection will be serialized as well with the closure. So the graph of this closure could become arbitrarily large. And that's, of course, a problem when those closures have to be shipped over the network to essentially all the worker nodes in your cluster. So a very, very large closure means that performance will suffer. So the idea here is you can avoid that as a programmer already now if you just make explicit what a closure captures. So a much better way to formulate this program here is to write do later like this, to say, well, do later, and then you pass a block, and you say, well, let me pull out the sum field here into a local variable s and print the s. So why is that better? Because with a sufficiently smart compiler, the compiler will actually figure out that that closure here doesn't have any dependencies to this class C. The closure is from here to here, right? It's just this last line here. And, sorry, it's just this last line here. So the closure just refers to a local variable, and that's just a single int that needs to be serialized. So the compiler will figure out, well, we don't need a pointer to the class C, and therefore the closure can be very lightweight. Okay, so that requires a compiler that actually does this, is smart enough to know about the dependencies, and that's something, again, that the Scala compiler team is working on to essentially get the compiler out there, to have a compiler that avoids these gratuitous references. There's still the question, well, how can you be sure? Because, of course, the transformation from that one here to that one here is maybe, again, not super obvious for a lot of programmers. So, again, you want help and say, well, look, this is a dangerous closure. A lot might leak from that. And there's a neat trick called Spores that can give you that. So a Spore is simply a macro. You call it like essentially a constructor. So you say Spore and then of the same thing. And all that macro does is it says, well, the thing inside a Spore will be a closure. And the only references in that closure that the closure is allowed to have must be two variables that are defined in the same Spore. So you can't have any outside references from a Spore. A Spore is in a sense a closed system that can be shipped to some other node without dragging a dependency graph that has to be shipped as well. That's where the name comes from. Okay, so Spores, I think, are a great idea, which would help a lot in all circumstances when code has to be shipped over the wire, and SPARC is one of the primary examples for that. Okay, second example is fusion. So at the last SPARC summit, Jay Oosterhout, she had a talk showing that essentially a lot of SPARC jobs are compute bound. So SPARC jobs are typically compute bound because SPARC does a very good job in keeping data in memory using the RDD abstractions. And that means that if we want to make SPARC faster, we have to essentially concentrate on the compute portion. And one thing we can do here is fusing. So lazy collections, as we've seen, avoid intermediate results. But they have still a large overhead because essentially every operation is a separate closure. So to do all these maps and filters, essentially we go to the closure for each element, and we go to the map closure, then we go to the filter closure, then we call them, and then they do something. What we would rather want is just a tight loop that does these operations as primitives, and that's what fusion can achieve. We had some very promising early results in the Scala Blitz collection library that used essentially macros to achieve essentially global fusion, and that got speed ups of, I think, a factor of 30 to 100 in many examples. So that was really very, very impressive. And we are currently working on a whole program optimizer that would have fusion built in. So once that is available, I think it can actually do a lot for compute-intensive jobs like SPARC. And the third one is looking a little bit further out, that's staging. So staging is an old idea. It has one of its recent applications came out of joint work by EPFL and Stanford. Stanford part is called Delight, where the idea is you have a lot of applications. You have a bunch of applications, and each of these applications would have a DSL, a query DSL, and SPARC could be one of them. And for each DSL, you would have a specific DSL compiler, and those compilers would map onto a large range of hardware. The hardware could be very specialized. It could be GPU. It could even be FPGA to really run your job much in the fastest possible ways. And all this is made possible in Scala using staging. So what staging does is essentially when you run a program or a query, then the first thing it does is it doesn't actually run. It constructs a representation of itself as a syntax tree, or more likely as a data flow graph. So it essentially gives you a graph that says, well, that's the way I work. And then you have a runtime compiler that actually runs when your program runs, or more precisely when your program starts up. And that compiler can construct an optimized version for your program based on the actual data workload. So the good thing is that runtime compiler actually sees your data set. It knows the size of your data. It knows the distribution of your data. And it also knows what target platform you're running on. So you say, okay, you're running on an Intel with vector computer. I do expressive vectorization. Or essentially, you can also say, well, I want to help with the GPU. The compiler can do that. So the targets then can be JVM, native, GPUs, FPGAs, and so on. And I know that AmpLab and Databricks are actually looking at staging as one of the techniques to make the next version of SPARC faster. Good. So I want to conclude with saying, well, how can we work each other? That was it so far. But the next thing would be to say, well, how can Scala and SPARC help a good cause? And there has been great work by Alexi and others to actually set up an initiative where we teamed up between the user groups as of Scala, as of SPARC, AmpLab, and Driver Group to create a community effort around open genomics. And the purpose of this community effort is essentially to make an open source system and ecosystem to help fight cancer. And we just put together a video that shows you how we propose to go about that. So I want to conclude the talk with this video.
David Patterson is a professor at UC Berkeley and wrote an op-ed piece in the New York Times. It was a call to arms that said, if computer scientists can attack the problem of cancer, then we have almost a moral obligation to do that.
Cancer is this terrible disease. We have the skills that could help fight it. How can we, as moral human beings, ignore this?
The cancer patient in 2015 lives in a paradox. There's never been more knowledge and more drugs to help that patient, but the patient's never had access to a smaller fraction.
When we started the ATOM project, we were looking at a lot of the computational problems in genomics, and a lot of them are patterns that map really well to a traditional ETL-like setup. ATOM is an attempt to think up a scalable API for processing genomic data.
What genomics is the process by which we take the DNA out of cells, DNA and RNA, all of the information, and we analyze it and convert it into data so that we can identify what has gone wrong in the cell. DNA is 3 billion letters long, and so what we do is we fish out that coding information and then we sequence it, and the output of that machine is basically text files that are about 100 letters long. And so then what has to happen from a big data perspective is that that raw data has to be reassembled into the original sequence. What we do here in this laboratory is that we take tumor samples from patients, we get a normal cell, we compare the genetic information in the tumor cells, and then we apply statistics and algorithms and our understanding about cancer biology. And what we're looking for are differences in that genetic information. We call those driver alterations. And this has revolutionized cancer care over the past 15 years.
OpenGenomics.io is a group of volunteers which wants to help defeat cancer faster through open source technologies and education for both biologists and computer scientists. OpenGenomics is a great way for developers in Scala and SPARC communities to give back. We work on very important problems in commercially successful companies. This is a way for you to volunteer and to help a really important problem of humanity. We had huge enthusiastic response from open source developers. They generally ask, how can I help?
If you really want developers who are experts in their own area to help out, you have to tell them what's out there, what the data sets are, and give them something that they can play with.
So, we try to make a strong effort in the Big Data Genomics project to keep everything open, to keep our plans for what we're doing open, and make it easy for people who are new to get up to speed and start contributing to the project.
I find it incredibly exciting to see Scala and SPARC to be put to such an extremely important use, saving lives. Oops, sorry. Lives.
It's very rewarding to see this technology already used in medical applications and in cases with real patients.
Through the patient-facing experience we're building, we're giving people direct access to their data and information that will empower them to seek the care they deserve. We're fundamentally changing the way that patients receive cancer care.
It's really exciting. I mean, you feel like you're on the forefront of science and discovery, and you're also helping people, which is awesome.
Most people today think that the next big leap forward in cancer is going to be a breakthrough in the future. We, in a very revolutionary, disruptive way, believe that the biggest breakthrough the patient needs today is an organizational model that gives them access to the breakthroughs that have already taken place. And getting the patients access to those breakthroughs, we believe, will be the biggest leap forward that's taken place yet in the war against cancer.
Thank you. Good. Thank you all. And I think we have a pause now, so we can talk more about this and other things then. Thank you.